Welcome again to this lecture about vertical scanning interferometry. So it's a microscopic technique, and one of the major purposes for us is to analyze surface reactivity. So basically, it's a technique that is quite ancient. It has been developed, I guess, in the late 60s, early 70s, and has been started to use heavily in the 80s, because with a surface-sensitive method, you are able to analyze surfaces fairly quickly and to figure out whether or not something is going wrong with this kind of surfaces. And one of the major motivations to use this technique was in the semiconductor industry. And it was a very precise method where you can analyze the surfaces and surface topography, deviations and aberrations. You will be able fairly quickly to analyze if anything is going wrong in the production process. So it was really focused on applied things, and not too many manufacturers were focusing on instruments in the material sciences. And this has been changed dramatically in the 90s. And dramatically is maybe not the right word, because it started really with a few machines in Japan and in the US, where people focusing on material science questions came back to this technique and said that might be a good idea to test something that we actually cannot really access. And now we come to the second part of the title. It's about surface reactivity. That's something I need to explain a little bit more in detail to you. So in the material science and crystal surface mineralogy people in the 90s, there was always a discussion about so-called reactive surface area. We are talking about crystal dissolution or growth. You normalize your rates to a surface area. And this goes back to the experimental approaches where you use powder material, you grind your solid material, put it in a beaker, and then you analyze the solute, and you get some information about dissolution or precipitation. And then you come up with changes in concentration, and you need a fudge factor, and this was surface area. And fairly quickly people figured out, yeah, from experiment to experiment with identical material and identical chemical and physical conditions, there are differences with respect to the kinetics of the reactions under investigation. So it might be something about surfaces that do contribute or not so much contribute, and they came up with the concept of reactive surface area. And when I was a student, all people say, yeah, we want to analyze reactive surface area values. That's what we need to do. But there's, of course, no technique to do so. And now I come back to the initial statement where some researchers in the US and in Japan took advantage out of this surface-sensitive method. They started to analyze directly what's going on crystal surfaces with the surface-sensitive method. And based on these fundamental investigations, 20 years ago, the concept of surface reactivity analysis came up fairly quickly. And this is something that is illustrated by this simple graph that I just copied from the Web of Science citation reports, where we have the number of publications where we can find in the abstract the words reactive surface area, that's the red thing, and then the combined sequence of words of surface reactivity. And you can actually see fairly quickly what happened during the past few years. And a large fraction of this kind of analysis and quantification is related to surface-sensitive methods. So let's start with something that I guess most of you have utilized already. There is some weird noise. Hopefully that's getting better. Okay, so let's have a quick look to the left side of the slide here, where we have two different phases of a zinc oxide crystal. So it's the 000-1 surface. So that's this hexagonal plane, and we do have one of the prism surfaces that's 10-10 surfaces. And we do have AFM analysis of the surfaces here, and the material has been dissolved and the material developed the so-called edge pits. So these are voids of the volume where material has been dissolved and released to the solution. And as a function of crystallography, you can see very characteristic shapes. So the hexagonal shape over there, and these triangular shapes from the 10-10 surfaces. And this was one of the examples where these initial investigations of AFM met surface sensitive analysis using vertical scanning interferometry, because the analysis of zinc oxide dissolution kinetics was based on that what is available on the left side, these observations, and people were not aware of the controlling factor of screw dislocations. That's something what is shown now on the right side, is much larger field of view, and this is an example that has been collected using vertical scanning interferometry. So the concept is almost identical. It's surface sensitive method, similar to AFM. Nevertheless, there is at least 2-3 major differences compared to AFM. For field of view, it's really big. You know, that's the minimum field of view size. It's about 100 by 100 micrometers and can be enlarged up to the millimeter range. Second thing is, with very high precision in the nanometer and sub-nanometer range, so sensitivity, vertical resolution is more or less equivalent to what we know from AFM, we are able to analyze the topography, the height of the material under investigation. So, large field of view, but identical vertical resolution. And another very important point here, it's a magnificent, really beautiful signal noise ratio that this technique does provide. And this led to a number of interesting applications. So it's not just about monitoring the evolution of surface topography. So this figure A, right side, upper right side, is dissolution after 16 hours, and then we have dissolution after 28 hours. And there are, if you look carefully, you'll see tiny little changes when you compare B and A. Because of the beautiful signal noise ratio, you can utilize this kind of data set to analyze with very high precision what happened in between these reaction periods. That's shown on the right side, where we have surface difference maps that identify the heterogeneity of surface reactivity. So now we are back to the initial question: what about reactive surface area versus surface reactivity, and how to identify the reactive portions of a crystal? This is something that has been largely driven, this kind of analysis, quantification, and parametrization of kinetic simulations has been largely driven by measurements using vertical scanning interferometry. And there's an example that illustrates what's going on the reacting crystal surface. There's these black portions where almost nothing happens. There are these tiny little blue colored dots. They refer to a specific defect type. And then we have these other characteristic circles where a lot, or the major portion of surface reactivity is doing the important work of material release. And by using this kind of technique, and that's the last point of motivation that I want to show you, it's one conclusion. That is something that is not that obvious. One important conclusion is crystal dissolution is not simply reverse growth, something not too many people would assume up front, but by utilizing this kind of surface sensitive data, you are able to dig a little bit deeper and revisit question of poor research. So it's not just about applied stuff that you can analyze what's going on with the material under investigation, dissolution, growth, sorption of nanoparticles, sorption of colloidal materials, aggregation of particles, or formation of thin films that are composed of cells, of transparent organic material. This is all kind of applications that you can track with this kind of technique, but you can also, because of the quantitative data sets, you can also tackle a lot of fundamental questions. Okay, so back to the basic physics. What's going on with interferometry and the physics behind this? That's really simple. That's physics 101. If you recall what you learned in high school, I guess this picture on the left side is quite identical to what you have seen. You need a light source to do interference pattern. You need a light source. The light beam goes to a beam splitter, and the beam splitter divides the light beam into two pathways. One of the pathways goes to a reference surface, and the second one goes to a sample surface. Both mirrors, so to say, reflect the light. The light travels back from both sides. The light does interfere. And the interference pattern is later on observed. Not just by your eyes here, it's observed with a detector, with a pixel camera, a CCD device. So simple thing, simple Michelson interferometry, cross-shaped approach. I'll come to the details later, but that's the basic principle. What does the detector see for each pixel of this grid? That's shown on the right side. If you have an optical path difference in between the two beams, from reference and the sample mirror, you come up with an interference pattern of constructive and destructive interference. That's the blue curve. And the second thing that you could do is, by using white light, you can just calculate the envelope of the interference pattern. That's the orange colored line. Okay, so that's what the detector does see for each pixel. In reality, things look a little bit more complex, but also much easier. It's a microscope, as it is shown on the left side, similar to a regular light microscope. You have the mechanics, you have your objectives, and you have a sample stage. I'll discuss later. And if you go now to the details, it looks a little bit different with respect to the light beam that is utilized here. The left side, it's still what we have seen. We have some LEDs where we can get monochromatic light, or we switch things together. We have white light available, and that's what is fed into the red colored beam path here. But there is one major difference. We do not have on the right side the reference beam, right? So it's just this beam that goes down here through the objective, and then we have here the so-called mirror interferometer. That's kind of an objective, as it is shown here on the left side. And the objective itself contains the reference beam, or the reference arm, actually, of your interferometer. That's visible here, but it's also enlarged at the left side, where you can see what I actually want to highlight here. So it's the yellow colored cone here, it's red colored here. And the beam splitter that we have seen initially here in the central part is actually located at the front lens of your objective. And there's this light yellow cone here, what illustrates now your reference beam. The reference mirror is sitting inside of the objective. something that's pretty weird. You put into a high quality objective something that will reduce the quality, but in that sense, it is required to do that, since we want to have the reference mirror at the same mechanical length as the distance in between the front lens of the objective and the sample is. Otherwise, we cannot do this kind of measurement. So that's the reason for small distance objectives, where we go quite close to the surface to collect a lot of light, to have a high numerical aperture of our objective, that we have to put the reference beam and the reference mirror inside of the objective. So that's the so-called mirror physics or mirror interferometer principle. For lower magnifications and larger distances, we do exactly that, what I have shown you initially, the more intuitive thing, where we have a reference beam that is rectangular oriented to the beam that goes down to the sample. The Michelson geometry, this is also available as an objective. You can see things here. Here, the green colored thing actually holds the reference mirror. What's the difference? It's a large working distance objective. The numerical aperture is quite low, and this will result in differences with respect to spatial resolutions. But sometimes you have to make a trade-off for one or the other. So what happens here is with the detector, that's similar to what we have seen previously. Here, pixel by pixel, we analyze the interference pattern. There's a third type of interferometer objective available. That's the so-called linear objective. That's a very complex system, since you are doing things a little bit, you have to introduce another objective. So it's not just a reference mirror, you introduce a second objective lens identical to the objective that observes your sample. But this is something that is of importance for analyzing fluid films, biofilms, something where you need to have control about the fluid chemistry. If you modify the concentration in a fluid, you're going to modify the optical properties. If you are doing this, if you modify the optical properties, you modify the optical path lengths, with serious consequences for your interference patterns. The linear two-beam interferometer is a way to do a hardware compensation, optical compensation directly. So if you put in something on top of your sample, an example would be the fluid film in a fluid chamber, you can do identical things with your reference objective, and you correct automatically for the modification, similar to a filter system that you apply to both beam pathways. So there's different measurement modes available, and this refers to the interference pattern with this dampening and the orange colored envelope curve that you have seen already earlier, a few slides earlier, when we discussed the general shape of this kind of instruments. The two types of interference patterns are shown on the left side here again. So let's start with monochromatic light. Could be red light, or it could be blue light, or yellow, green, something in between. So what does happen with respect to your interference is shown in the upper figure. You produce constructive, destructive interference as a function of wavelength. If you have multiple wavelengths included, you are going to superimpose things. This happens when you use white light in contrast to monochromatic light. As a result, the shape of your fringes are highest at zero order situation, and there is a dampening towards both sides. That's the first order fringe, second order, and so on. And this is this envelope function that is available here. And for vertical scanning interferometry, two types of lights are utilized as a function of the application that we are going to have. So this identification of the zero order fringe out of this kind of interference pattern is quite difficult. This applies for both for the monochromatic and for the white light, because the differences in intensity are not as high that they can be detected fairly quickly. So remember what the machine will do when the reference when the sample surface is scanned. It has to detect the intensity as it is shown here in this interference pattern. So with a high-speed camera, you have to detect all the amplitudes, and then you have to compare whether or not this intensity is really bigger than this. And imagine you do not measure things here, but here, just a few nanoseconds later, and then it might be quite difficult to identify the zero position. And this is the motivation for white light interferometry to analyze just the orange colored curve over here. So you sample a few intensities, usually it's just half a dozen or so of the intensities, and from that you calculate the orange colored curve. And this is quite simple and fast to do, and we come up with this kind of shape based on a few simple intensity measurements. This also provides the opportunity to scan very long changes in surface topography at a decent time frame. You know, here's an example for 100 micron height difference. You can do that in a couple of seconds with a high-speed camera. And you do this for all pixels at the same time. You compare this to an AFM measurements with all the artifacts that can happen. Then you see the differences with respect to applicability, field of view, sensitivity, fast, all kind of stuff. So that's one thing. So it's more reliable to compute the envelope, the modulation of the fringes, and determine this kind of peak. And you can really pump this up. You know, you can have scan length of up to several millimeters, and it still is a time frame that is quite okay. Of course, what has to be done, you have to take care on the environment, and you need a specific optical table where you put on your instrument, where you provide some conditions that sustain this kind of high precision in the nanometer range. So there's a second mode of measurement, and this refers to the monochromatic light. And this is called phase shifting interferometry, in contrast to white light interferometry. So both measurement modes are vertical scanning interferometry. Usually you can switch back and forth in between the two modes. You might have to calibrate things from time to time, but you'll be able to do the two measurements with a single instrument. So what's going to happen here? With phase shifting mode, you utilize monochromatic light with increased coherence length. And the increased coherence length is responsible for the different shape of the intensity pattern. Higher coherence results in an interference pattern that shows lower dampening compared to the white light interferometry, as it is shown here in the lower right. What I mentioned already is it might be a little bit different to distinguish or to discriminate between zero order, first order, second order, and so on, if the intensity pattern is so similar. And this provides one of the constraints, the physical limitations. What you can do by using phase shift interferometry you can detect the changes that are constrained by the two green colored lines here. You'll be able to analyze height differences that show a range of about lambda divided by 4. So that's this section here. They are responsible for this kind of phase shift. Nevertheless, the precision is 1 order of magnitude higher than that what we have seen with white light interferometry. And for several applications, this limited height range analysis is still sufficient to come up with very interesting and important data sets. You know, we are working here with a precision that is able to detect height changes of a single crystal layer. That's really something where you can track fundamental changes of solid materials in a very high precision. Again, what cannot be done is the height differences, the height modifications that go beyond this height change that refers to a quarter of lambda. And this is illustrated by this little example here, where we have monochromatic light on the left side and white light on the right side, and where you can see fairly quickly the right side that there is some slope included, slope that is superimposed to the step surface, to the stepped surface that is analyzed here. So the step height can be analyzed fairly nicely with monochromatic light, but the slope that includes much more topography changes is not visible. Okay, so now that we know the basic principles, basic limitations, we should have a look to how the reality looks like. So here's an example. That's a surface that is quite irregular, and a sequence of interferograms, a fringe pattern, is shown on the left side here. It's not just a simple camera, but it's shown here for illustration, but the principle is quite simple. You know, what is done here on the left side is just to store the live images of the interference patterns. So it's not the analysis later on for reconstruction of a sequence of interference pattern and to calculate the height distribution from one fringe to the other. Here it's just a sequence of live images. And the interference pattern looks quite complex. Here's an example. You can see these white and black lines that form these irregular shape. And for all the positions where you do see the black and white curved lines, you are more or less in focus. And when you scan through your surface, you can also see by moving your objective downwards, or if you lift the sample a bit, the fringes move to the central part of this hole. Going to this section here, and here we reach the bottom already, and here we are close to the bottom and go with the focal plane below the material, and then no more fringes are visible. And this sequence of fringe pattern is stored and analyzed for the differences in the fringe pattern, the differences of the distance of the fringe pattern for each pixel. And from these differences in distance, the height differences are later on calculated. So now that we have the material, we have the fringe pattern, we want to have a sample and put it on the sample stage, and we want to do something with the sample. What do we have to do with the sample? There is some basic requirements. It has to have a minimum reflectance because we are working with light. So we need reflected light. And the second thing that we have to maintain is that over the entire sample surface, the contrast in reflectance shouldn't be too high. Why? During the measurement, we cannot modify the light intensity. This means if there are a few portions with low reflectivity, they would probably provide an intensity pattern that might fall below the signal noise ratio of your camera. There's of course also some hardware corrections around in modern instruments where you modify the light intensity to circumvent such behavior. But usually if you want to have a simple measurement, you would provide more or less continuous reflectance of your sample. If this is not available, or the reflectivity is too low, you can do at least a post-mortem analysis. You can cover the surface, you can spot the surface with, as an example, is gold or palladium, and you could then do at least a post-mortem surface height analysis. Much more interesting is in situ or near in situ analysis of what's going on. So there's two ways to do that. You can utilize objectives that are objectives that can work in fluids. So you can do your analysis by tipping your objective within the fluid. Nevertheless, there's another constraint with respect to the numerical aperture and the resulting spatial resolution. It's not as high as it is for objectives that are constructed for working in air. And this is the motivation, if you want to have higher precision, that you do this near in situ approach, what I would like to show you here on this figure on the lower right side. So what is available here? We have the objective, scheme of an objective, and we have a flow-through cell. This flow-through cell can be mounted on the sample stage of your interferometry. Input of the fluid, you have a scavenging pump port to remove the fluid, and you can react your sample. That would be the little blue object that's sitting below the objective and the optical axis, the optical path O. If you want to do your measurement in this near in situ thing, you can remove for a few seconds the fluid film by pumping the fluid away, dry your sample with a nitrogen gas stream, do your few seconds of measurement, and then you continue with a reaction. Of course, this is limited to, again, to some specific applications, but for all applications, you can do this kind of experiment. It's not a real in situ, it's near in situ if you need the precision, if you do not want to utilize the real in situ objective. So what do we learn from that? We come up with a sequence of surface topographies. Here's an example. Experiment has been done over more than 5 hours. I guess 50, 80 maps of the surface evolution have been acquired. And with this kind of data set, you can go ahead and analyze what's going on with the surface. You can provide a movie to see the changes. It looks beautiful. It might not provide too much details with respect to the basic mechanism. We'll revisit this point in a second. Important thing I want to highlight here is this is even larger field of view than the example I showed you initially. So this is more than 1 square millimeter of surface topography that has been analyzed. So how does the instrument look like? You have seen the example on the right side already, but there's also different types of constructions around, and I would like to explain a little bit what are the basic constraints. So we need mechanical stability. You know, we want to do nanometer or even sub-nanometer precision with respect to height analysis. So this requires mechanical stability, and that makes things more difficult compared to a regular microscope. Second thing is sample stage. I showed you already, most people in material science wish to mount a reaction cell on the sample stage. So this is something that can be done fairly easily. Most of the instruments are capable to carry a few hundreds of grams of material on the sample stage, so you can connect your fluid cell and the connectors and the pumps sitting on the table to feed your reaction cell with fluid. So that's easily doable. Second thing is to talk about the objectives. So magnification in numerical aperture is one thing that I mentioned already. For white light versus monochromatic light, you can use identical objectives. Nevertheless, you have to be able to correct the position of the reference mirror, what is sitting inside of the objective of a mirror construction. That means you have to be able, if you think about your experimental setup and fluid cells sitting on the sample stage, you have to be able to reach the objective. At least for the higher magnification objectives, you have to correct for that if you change from white light to monochromatic light. With green light, it is okay because it's in the central part of your emission spectrum of white light. If you're working with blue light to enhance the spatial resolution, you have to correct for the reference mirror position if you are switching back and forth in between the two measurement modes. There's another important point, that's the tip tilt correction. So the orientation of the sample stage, and much more important, the orientation of the sample surface under investigation is a very important point. Quite often overlooked, and then people are measuring something, then later on, oh, I need to correct for the orientation of my sample, and I will do that via software analysis, via software treatment. What is a pretty bad idea, because this is not a tomographic system. You know, we get XYZ data, that's for sure. Nevertheless, we're observing things perpendicular to the sample surface. So it's rather a 2.5 dimensional data set than a 3-dimensional data set. We'll come back to this point. Okay, so what can we do? We can have a qualitative watching, the movie that I told you. We can combine the data sets with other topography data. An example would be a tomography method, tomographic method, micro-CT, microcomputer tomography, where we could combine the geometry information that has been collected with interferometry with the low resolution data that CT data provides. So that's one thing if we are just interested in surface evolution. Second thing to do is statistical analysis of height data. And that's the point to visit, at least for a few seconds, the topic of surface roughness analysis. And the second thing is something that I like much more, because it provides direct insight into the quantitative evolution. That's the calculation of rate maps, and to do a statistical analysis of the rate data that can be directly derived, calculated. That's what I would like to start with, since you have seen half of the story already. So that's another example of a reacting surface on the left side. That's the starting topography at t = 0, and that's after a corrosion of 8 hours. And what is important is to provide an inert mask as a reference surface. And with this reference surface, you can recalculate for all the other XY couples of your data set what happened to them during the reaction from each measurement to the other. We can calculate height different maps for each XY position. You get a velocity, so that's a change of height per reaction time. And by dividing your height, actually not the height, the velocity, by dividing the velocity by the molar volume of the material, you end up with the rate. And that's something you can compare to the data sets. You know, rate data that have been collected with other approaches. And that's a quite important thing, since then it makes a lot of sense to compare the height, the rate variability that you can observe with this kind of data set. So that's the rate map that is available for this kind of example. And then we can do an analysis of the rate contributors. So this is the rates versus rate histogram versus frequency. We come up with a contribution of different components that form the overall reaction that has been observed. And that's the point to connect to the other kind of analysis of topography data. That's the analysis of surface roughness parameters. So we should keep in mind what's going on with these surfaces. If we talk about growth or corrosion, we have to make clear that we know what are the basic reactions with surface building blocks, point defects, screws, grain boundaries are included here. You know, screw dislocations, edges of the crystal terraces. They provide another coordination. They will come up with another reactivity. But that's something that can be analyzed. So, but you need to keep this in mind for any roughness calculations. What are the critical height ranges to be investigated and compared? And I have a statement that might be kind of provocative. Most roughness data in literature are useless, and especially the comparison. So if someone shows, oh, I have roughness range 1 compared to 2, they look different. There is something behind that. You know, if you do not have the details that we will discuss in a second, then you do not learn too much. And it's not just wrong to compare these things, it's really misleading. So it's, again, you have to make clear what is the basic reaction that you are going to investigate and what height range is included. So is it crystal steps, or is it another kind of defect, screw dislocations? And then you can go ahead and compare the height differences by utilizing your parameter sets of surface roughness. So of course, if you have the data set that we have seen previously, and you will see, oh, there's large changes in topography here, compared to this position here, we do not have that much changes. Is there any information about surface reactivity included here? Yes, for sure, but it's not just a simple comparison of a roughness parameter. So let's talk briefly about surface roughness parameters. Why do we have them available, and what can we learn from them, and how is a proper use done? So it really dates back to the 30s. It's really ancient. And of course, you made the interpretation fairly quickly. It's based on other types of techniques that are much older than that what we are discussing today. This is so-called stylus instruments, where we have a needle instrument, and this is moved over the surface, and simultaneously you record what's going on with the surface. And this kind of measurement was quite simple. It was a glass plate, and this was smoke from the product of burning oil and tobacco. So imagine the smell. And from these data sets, you can quantify amplitude distribution, and you come up with a statistical treatment of these curves. Here's an example. The most common used roughness parameter is the average roughness parameter, RA, and it's quite often compared to the peak valley distance, RT, in that sense. So here's an example. Here's a profile of a rough surface, and there's no dimensions shown here. And it doesn't really matter if it's kilometers or nanometers. So if we would calculate things, we'll come up with an RA of 42. If that would be microns, that would be microns, it would be 42 microns, and a roughness depth of about 200. Then you're going to analyze the second topography, and topography profile looks like that. And maybe some of you are pretty tired because it's time to have a nap. I could ask the question, what do you think about average roughness parameter, RA, left side versus right side? Is it higher or lower? What's your best guess? Does this topography look more rough compared to the right side thing? As always, also here, the answer of the difficult question is again 42. So we have a roughness of 42, in this case microns. Roughness depth, RT, is just half of that what we have seen here. So if we now go ahead and compare things and come up, oh, there are identical average roughnesses available. These surfaces behave identical. This might be a good interpretation, but might be also difficult. So there's a second point that we need to touch. It's about so-called converged roughness parameters. So there's a lot of parameters around, and for comparison, you also talk about the superimposition of different surface building blocks. And that's something that's really important if you're going to analyze your surface topography data. And this little scheme in the central part actually illustrates things quite nicely. Imagine you start with a cylindrical surface, that's the nominal shape, and the cylinder has been formed by any kind of process that leaves a small scale variability, that's the waviness. And the third order variability, that's the so-called roughness. So in that sense, if you want to talk about roughness and surface shape and surface variability, it's about the wavelength of aberrations. This is something we have to keep in mind, how the concept has been introduced. It comes from material science, production of material, steel material. There is friction of steel material. It is used, it has been applied to some mechanical treatment, and then people want to compare what has been changed. So that's the basic motivation of a surface roughness parameter. If we want to see whether or not this kind of variability of the surface is really meaningful, we need to extract this tiny little section. And for this example, like it is available here, you would say, oh, it's a quite simple thing. Let's just do a Fourier analysis. We come up with a frequency distribution. That's quite simple. Yes, but for natural systems, for reacting, corroding materials, it's not as easy as for machine ones, and there might be no regular distribution of this kind of aberration. Then you have to do things manually and split your field of view size down to little subsections and compare whether or not you have a plateau situation of a surface roughness parameter. And if yes, then you can utilize your surface roughness parameter for comparison. So what that means is it constrains two basic physical constraints. Its left side is, of course, lateral spatial resolution. This is the smallest details. And the field of view size is what you utilized for this kind of manual convergency approach, where you minimize the field of view in a well-defined way. So in the end, it's a bandwidth, bandpass system, and you define what range of wavelength variability is quantitatively analyzed. And this provides then a means of comparability. So there's hundreds of surface roughness parameters around. Don't want to talk about them. There are a few groups available that you need to know if you want to apply them. We have talked about the amplitude, but there's also some spatial property analysis parameters available. But wait a second, it needs some information about periodically or non-periodically distributed surface features. And there is parameters that you take direct quantification of surface area and volume portions of the topography. It looks like that. If you analyze your stuff, you can utilize the software that is built into most data collection software packages that are available with these interferometry instruments. And then you can go ahead and analyze things. And in the last few minutes, I would like to show you one very simple example of a regular grid pattern, just to get a better sense about how data sets would look like and what analysis can be done and how things are done in a more practical way. So this is a simple surface pattern, a machined one. It has a regular structure. And of course, for them, you can do all those things that I mentioned earlier. You can calculate orientation. You can calculate a grid pattern, the grid, the constant length in X and Y direction, what is shown here. And big surprise, they are quite similar, 1 micron in X, 1 micron in Y direction. And we can come up with quantitative data focusing on the height distribution. That's shown here on the right side, where we have a height histogram. And I introduced 2 limits to the lower section, the blue stuff here, and to the higher portions of the height. That's the red sections here. And then you can utilize this kind of data set to calculate the mean height of the surface bumps that are available. But nevertheless, there's also some data points available that refer to deeper heights and higher heights compared to your bumps. What's the reason for that? There might be bending or tilt of the surface topography. If you have a quick look to this section here, more blue color here compared to this one here and here, it looks like the surface is bended at the nanometer scale. So then you can go ahead and utilize these beautiful surface roughness parameters that I introduced to you in a rather unusual way, so that you have to be a little careful with them. And you can calculate these height distributions using the arithmetic mean. That's the SA or RA. If you do it for profile, it's called RA. For a surface, it's called SA. Or you could also do the standard, calculate the standard deviation of the height distribution, RQ, or with the XY data set, it's SQ. Peak height, and there's another calculation to analyze the height range. That's a so-called 10-point height. That's not that sensitive to outliers because it summarizes the local maximum values of the 5 highest and 5 lowest surface portions. Now I am going ahead and modify the surface a little bit. I just cut a few sections, a few portions of the data sets, of the data set that has been analyzed. So the maximum height is about 800 nanometers. And what I do, I just limit the height in steps of 200 nanometers. So I just cut the uppermost 200 nanometers and do this again. What's going to happen with the parameters? Again, is roughness, nanometers, and this is the maximum height. And as you have expected, there's of course a different behavior of SA versus SQ versus the overall height range. And if you compare this to the surface area that is analyzed by this technique, you can also see that there is some first order correlation, but there's just some deviation from this first order correlation. So that's also something we need to discuss, what's going on with surface area. But before we do that, I will show you something that is of critical importance for the practical use. So that's about the background topography. If you introduce a slope, as it is visible here, of course, you come up with some modification of your roughness parameters because they are affected by the overall range. But that's not the important thing. That's something you can correct for. And actually you have to do so if you want to compare things. The other things is the tilt correction that is done after the measurement by using your measured data sets already. So this will end up with artifacts. Here's an example. I show you as an example this red arrow, more or less in parallel to the bottom line of this pit. If we're now going to rotate things here and really key this orientation of the red arrow constant, you actually see what's going on here. And I'm no longer in this kind of position as I have shown it here, since it's not a rotation, it's a projection. What usually is done, there's a good motivation for that. If you would rotate your data set, you would come up with a grid with your pixel size that would vary. Cannot do that because that's too difficult to handle with most software that is available for that. So it's still stupid projection. That's something you should keep in mind. So surface area, what is done here, and how is that related to surface roughness parameters? That's a pretty, practical parameter set that can be used. And there is also some, sometimes it's several words are used for identical things. So the surface area is expressed by the surface factor. You can say, okay, the projected area or line, the blue line here, is enlarged by a factor of X because of the topography that has been added. So that's the uppermost line here. And if you calculate this enlargement factor, this is sometimes just referred as the roughness factor, or as a percentage, as it is shown here, it's shown as the surface difference ratio. Now, in the end, it's quite simple. You have the length of this profile, it's a rope. You pull this rope, you come up with a length that's much bigger. You divide this gray line divided by the blue line length, and then you come up with a factor that can be utilized here. Okay, so let's just summarize things and put it into a context of different kinds of surface sensitive techniques. So in the end, what one of the major motivations is it's with interferometry. It provides a very high vertical resolution. There are also some issues that I did not discuss today with, steep surface flanks and artifacts that can appear. That's something that really depends on your kind of sample material. But it's really fast, and VSI covers a large field of view. And with a large field of view and the pretty high surface resolution with respect to height, that's really important for a lot of applications. And it's very fast. That's always a point compared to the others. With SEM, you could also do 3D measurements if you analyze pairs of data sets, but compared to spatial resolution, because of the error that is introduced, if you have this parallaxis introduced, that's much less with respect to spatial resolution when you compare things to interferometry. Focus detection is another optical instrument where you have lower vertical resolution, but it's of similar field of view. Is also quite fast, but it depends on the question that you have available with respect to height resolution. And with the stylus techniques, that's quite difficult because it takes a lot of time. It's a contact analysis for areas. It's very beautiful for thin films if you want to analyze the thin film thickness, but for XYZ data sets, it takes a lot of time and it's not really feasible. So I hope I have been able to provide you at least the basic physics of VSI. I hope to explain some constraints of practical use, with the large length scale range and very high resolution. We discussed the critical importance of, to really understand what's going on with this kind of data set, since it's not a tomographic data. It's XYZ data, a very specific. And you should keep in mind what to do with this kind of sequences of surface data sets by analyzing them using time-resolved data sets, or just having some information about topography, and then you try to introduce some statistical analysis by doing surface roughness calculations. So if you have any questions left, I'm happy to answer. And yeah, that's for the kind of lecture, but if you have questions, I'm open to answer your questions. Thank you.